Welcome back, everybody. This is our video solution to problem 4 from Quiz 5, Spring 2023, Math 302 at Cal State Fullerton. And in this video, we're going to talk about the fundamental theorem of arithmetic. So let's begin. We got a long problem here. So it says, suppose we wish to show that the real fifth root of 7, right, i.e., okay, we got this notation for the fifth root of 7, this is going to be the real version, is an irrational number. Okay, so we want to show that. We proceed by contradiction and assume that there exist relatively prime positive integers a, b, such that the fifth root of 7 equals a over b. Okay, so we want to show it's irrational. We're going to assume that it is rational. If it's rational, you can write it as a fraction, a over b, and you can even assume then that you've reduced a over b, right? And by reducing them means they're relatively prime. Okay, we raise each side to the fifth power, and we obtain 7 is equal to a to the fifth over b to the fifth. Okay, multiplying by b to the fourth. Now that's a little strange, right? And you probably expected me to multiply by b to the fifth, but nope, I multiplied by b to the fourth. And I now get that 7b to the fourth equals a to the fifth over b. Okay, now b is an integer. Raise it to the fourth power, still an integer. Multiply it by 7, still an integer. So 7b to the fourth is an integer. And of course, b was positive. 7's positive, right? So everything here is positive. So we could even get a positive integer. Yay. Use the fundamental theorem of arithmetic to prove that b equals 1 and then find the contradiction. Okay, well, the fundamental theorem of arithmetic, this is telling me that every integer, right, and we'll just stick to positives for now, every positive integer greater than 1 can be written uniquely as a product of primes, where, of course, if it is a prime, like that's it, that's the whole product. Okay, fine. So that means that A has a prime factorization, B has a prime factorization, and those prime factorizations are unique. All right. We also know, though, that if I take a to the fifth divided by b, I get an integer. How can that happen? When you have a fraction and it equals an integer, that can only happen if the denominator divides the numerator. So a to the fifth over b is an integer, implies that b divides a to the fifth. Now, if this is true, then by the fundamental theorem of arithmetic, we know that every prime factor of b, well, certainly divides b, but then it must also divide a to the fifth. And then that's going to mean it has to actually divide a, right? So let's see how that works. Okay. If p divides b, where p is prime, okay, and of course we know b divides a to the fifth, then p divides a to the fifth. Okay, and well, where are we actually using the fundamental theorem of arithmetic, right? Actually, let me move this down here for a second, right? Because we're not quite using it yet. Okay, so this is true, but now, if p divides a to the fifth, well, what does a look like, right? A has some prime factorization. Okay, maybe we'll call it q1 to the alpha 1 through qn to the alpha n. Okay, where q1 through qn are primes, and alpha 1 through alpha n are positive integers, right? Those are how many times those primes occur in this unique prime factorization. So now this implies a to the fifth is equal to q1. Well, you have to raise everything to the fifth power, but that's just going to be to the 5 alpha 1 qn to the 5 alpha n. And again, by the uniqueness part of FTOA, these are the only primes, q1 through qn, that can occur in the prime factorization, right, of a to the fifth. But these are the exact same primes that occur in the prime factorization of a. Okay, so by the uniqueness of prime factorization, if p divides a to the fifth, right? So if it's one of these q's, then it also has to divide a. Then p divides a itself. So we've now concluded, so this implies that p divides both a and b, right? We have p divides a and we have p divides b. And this contradicting the assumption that a and b are relatively prime. Their GCD is 1, right? You can't have a common divisor. Okay, now where does this contradiction come from? Well, we made this assumption, right? We said if p divides b. Well, I mean, isn't there a prime that divides b? Well, maybe not. There is one way out, right? The only positive integer that does not have a prime divisor at all is 1. So since 1 is the only positive integer without a prime divisor, we conclude that b equals 1. Okay, now let's go back up to the problem. If b is equal to 1, then we can simplify this expression here quite a bit. Right? If b is equal to 1, you're just going to get 7 equals a to the 5th. So this implies 7 equals a to the 5th. And this is a contradiction, since 7 is not a 5th power. Since 7 is not the 5th power of an integer. Okay, so in either case, we are able to get a contradiction. Okay, and that finishes the argument. All right, everybody, we will see you next time.